Math 2414, sequences, video 8, the squeeze theorem, also known as the sandwich theorem. This is a theorem that you've probably heard of in Calculus 1, and you may or may not remember it, because it was a theorem that was talking about limits. Well, we're talking about sequences converging to a value, which is essentially asking for a limit. And so it stands to reason that there's an equivalent version of the squeeze theorem for limits, for sequences. And it goes something like this. Suppose an is less than or equal to cn, which is less than or equal to bn, for all n greater than or equal to capital N, where n is some positive number. Let's translate that mess for a second. What we're saying is we have three functions, three sequences, if you will. And at some point, in other words, once you go past a certain number, one sequence is always sandwiched between two others. It's got something below it, and it's got something above it. Now, it may not happen initially, but at some point when you cross some value for n, you have this double inequality, this Cn being between An and Bn. If the sequences An and Bn both converge to some limit L, then the sequence in the middle, Cn, must also converge to L. And visually, this kind of makes sense for the following reason. If you think of a sequence as part of a graph, just the dots on a graph above 1, 2, 3, 4, etc. Let's say that An is, first let's get a sketch of the graph going here. Let's say that An is green. And we have some dots here, and let's go ahead and set up a limiting line. You know what? Zoom can really draw good lines if I click on this thing. Vertical line, horizontal line. And let's say that we have a limiting line and we'll make it blue. We'll put the limiting line. Let's say that An is some sequence in green. So we'll put a green, excuse me, it's still drawing lines. Highlight. Say An is some sequence in green. So we have some dots that are getting closer and closer to the blue line. So let's say that those dots are, we'll use a heart, yeah. Say those dots are here, so 1, 2, well that's not very green. Am I gonna make the hearts green? I guess not. Oh, well, so much for that idea. Let's just draw dots then. Let's say that An is a sequence of dots that may go above the blue line, but let's say that they're below it and eventually they'll come up to it from almost like a sine graph, but then it's got an asymptote there. And let's say the B's are some pink dots. I like that. Say the B's are some pink dots. So, which may be above or below the ANs. They say they might be on them, but at some point they're above and they stay above. Let's say from this point forward, the pink dots are always above the green dots. And let's say that we have a third sequence, and we'll make these, what's a good contrasting color? Red. Highlight, please. Let's say that we've got a third sequence that at the beginning could be a between, or it could be above them all, or it could be below them all. But at some point, and let's say this point is here, here's capital N. Let's say at some point, the red dots stay between the green dots and the pink dots. Doesn't really say how close they have to be. Let's say after a certain point, that point being capital N, the red dot will stay between the green dot and the pink dot forever. Let's get rid of that highlighting. Make note that it happens after this boundary. If the pink dots are going to converge to this blue line in the middle, which we had called our limit, so we'll put L here for limit. And the green dots are also going to go to that line, and the red dots must stay between the green and the pink. Then it stands to reason that the red dots have to converge to that limiting line as well. That's all the sandwich theorem is saying. If you got a term of the sequence that you can sandwich between something that is always larger than it at a certain point and something that is always smaller than it at a certain point, and the two extremities converge to the same value, then the guy in the middle has to do the same. Now, a lot of times this inequality will hold from the beginning. In other words, sometimes the red dot would always be between the green and pink dots, but it doesn't have to be. It only has to eventually be. All right, so let's take a look at an example. Find the limit of the given sequence. an equals cosine of n over n squared plus 1. Trig functions are tricky when you don't fiddle with their period. The period of cosine is 2 pi, but our n is running through integers, and so you'll never hit any two integers whose difference is a multiple of 2 pi. In other words, it's impossible for cosine of n to be repeating, because if it did, for example, let's just say that we put in cosine of 1, and then eventually we got, and we had cosine of 2, and then we did this for a long time, but eventually we found another number that was equal to cosine of 1, the cosine of another integer, if you will. So for example, let's say that cosine of, 31 was equal to cosine of 1. It's not, but let's just pretend that it did. I'm going to say that means that their difference has to be a multiple of 2 pi, but that's not entirely true. Okay, let's just not go down that path because I painted myself in a corner that I'm not ready to get out of. My point is, the cosine of n, where n is an integer, is not predictable. In fact, it's chaotic. I'm not going to get into the definition of what it means for a sequence to be chaotic, and I haven't studied chaos theory in a while, but I'm 99% sure that the sequence cosine n, where n is an integer, is chaotic. All right, so let's get a bunch of points up here. N equals 100. All right, so if you look at these dots, you may be thinking they're all on a cosine curve, and you're correct. But if you were to look at their y values, this is the y values represent sequence. There's a y value, there's a y value, there's another, there's another, there's another, there's another. And it's a big old mess, and we really can't see a pattern in there. However, we're going to make a table like this. And if you were to look at the, give me another. There we go. All right, so my point is, when you take cosines of natural numbers and you look at the y values, there is no pattern, besides the fact that they're all cosine of consecutive integers. They don't converge anything. They'll never repeat, because if they did, then we would have evidence that pi is a rational number, which it's not. So we can't do anything nice with cosine of n. That's really what I'm getting at. That if you're dealing with cosine of n, it's going to be ugly. Now, if it were pi n, that would be different, but cosine of n by itself is just a train wreck. So what do we do with this? Well, the answer is we play the squeeze theorem on it. Now, how do we play the squeeze theorem? The way you play the squeeze theorem, and this is worth typing, use the squeeze theorem. You need sequence that is less than an and a sequence that is greater than an. And you need those two sequences to have the same limit. So it's a lot to ask. Let's sandwich this guy between a couple of sequences that will go to the same place. Now, before I take you down this path, I want you to intuitively think about what this limit might be, what this sequence might converge to, by asking yourself, what does the numerator do? Even though I just said it behaves a little chaotically, it is bounded, if you will. Think about the graph of cosine. It can only go so far up and so far down, versus what the denominator will do as n approaches infinity. Well, the numerator is stuck. You can't get so high or so low according to the graph of cosine, and the denominator is going to explode. So what do you think is going to happen in this fraction? Let's find out. Now, in order to sandwich this, we need to focus on the numerator in this particular example. You know that cosine has an amplitude of 1. It can only go up to 1, go down to -1, which means it doesn't matter what we put inside the cosine function, as long as it's a real number. Yes, you can put in imaginary numbers, values outside of that range, but let's not go there. As long as we take cosine of a real number, it'll always be between 1 and -1. Well, if we divide this by a positive number, it's going to preserve the inequality. N squared plus 1 is always positive, so we are within our rights to do this. And what we've just done is squeezed our given sequence between two other sequences. Namely, we squeezed them between this sequence and this sequence. And now we look at those and hope that they kind of do the same thing. And it won't take too long to see that they do. Draw. All right, the limit as n approaches infinity of -1 over n squared plus 1 is equal to 0. Any constant over an ever-growing denominator will collapse to 0. Or rather, I should say a denominator that approaches infinity. And the limit as n approaches infinity of 1 over n squared plus 1 is also 0 for the same reason. The top is the top is static, it's 1, but the denominator is continually growing to infinity. Since both ends of the inequality converge to 0 and we've sandwiched cosine of n over n squared plus 1 between those, the conclusion that we can draw, therefore, an approaches 0 of the squeeze theorem. So the trick for the squeeze theorem is to find two things to sandwich your function between and hope those two things both go to the same limit. Now, coming up with the lower and upper bound, if you will, lower bound being the one that it's greater than, and the upper bound being the one that it's less than. In other words, this guy is greater than its lower bound and lower than its upper bound. It takes some practice to be able to come up with things, but usually you start with some inequality like we did with cosine, and then dress it up to look like the sequence that you're trying to analyze. Right, so that's actually it for this one. So hopefully this will help on some of your homework.